right, this screencast I'm going to talk about the polarization of light lab. A few big key ideas before I get started, and that is that we can think of linearly polarized light as the sum of counterclockwise and clockwise polarized light. Better said, as right circular and left circular. And then corn syrup is a chiral molecule, so that it is it, so it literally rotates as a molecule, and some of it rotates right, and sometimes some of it rotates left. Now, where we expect an effect then is if the right circular molecules rotate at a different amount than the left. And that's what we're measuring is how much difference in phase shift the light experiences between the right polarized and the left polarized. So basically, the longer the path then that we travel, the more difference between right and left polarized that we would expect. And so the question we're asking in this lab is how does the distance the syrup travels affect the phase shift, or better said, the angle of polarization. So as chiral, some syrup molecules will rotate clockwise, some counterclockwise. However, the light may not rotate the same in each direction, and then a phase shift occurs. Now, what's interesting is that phase shift and index of refraction are directly related, where the more a substance shifts something's phase, the more that the greater its index of refraction. If we've got the right circular shifting at a different level than the left circular, we're going to have a difference in index of refraction between those two types of molecules, which is really interesting. The fact that we can have that within a single substance. We know that the phase shift translates into a change of angle of polarization, whereas the greater the shift, the greater n will be. So if our right polarized and left polarized have different phases, they'll have different indices of refraction. L is the distance that we travel in an optically active syrup, and we know that the difference in n is the index of refraction of the right polarized and minus left polarized. And then delta n equals change in that angle, the angle of polarization, times lambda divided by L and pi. The change in angle then can be, just algebraically manipulating that, is delta n times L times pi divided by lambda. Kind of what we're doing is we're putting, I believe we started with a horizontal polarizer, and we polarize it horizontally. If there's no optical activity, all light should come out horizontal. However, if there's a 180-degree phase shift, then it should come out vertically. And that's what we're measuring, is really how much does this corn syrup affect our measured optimal polarization, and that's the deal there. Our apparatus, we had a laser which we shot through the typical 2-mirror setup, which we put through the first polarizer, horizontally polarized, I believe, and then through varying lengths of syrup, and then with the second polarizer, which we adjusted until we had optimal or the greatest intensity of light on our screen. I believe actually it was a sheet of paper we used, and we just did that by the naked eye. The containers themselves are birefringent, and we learned that means is that they themselves cause light to refract. So there's some change just in the containers themselves. So to account for that, what we did is that we subtracted the phase shift with the corn syrup from the amount without it. So we had we filled up the corn syrup up to a certain height, and then a couple inches or so, and then we shot the laser above it to get the baseline, and then we shot it through the corn syrup and the plastic, obviously, and then we found the difference between those, so we found that, it said the lambda wavelength is 532.8 nanometers. What we're doing is so we collected our data, and I'll show that here. Um, so we got lengths, then we had our control, which no matter how many containers we had, they all had about the same um, birefringence level. Minimal difference is what we measured, and then our syrup value for how much maximum or the optimal polarization for the syrup, and then we just subtracted control from syrup, or syrup from control, and then I want to go back here and show. So we're plotting length times pi divided by lambda versus the angle, the change in polarization from horizontal, and that was and then you can see that. Oh, wrong one. There we go. And that is calculated out right there. So L times pi divided by lambda. So pretty big numbers because lambda is very small. One thing to point out though is our data. I know you saw my original data. It was just kind of funky looking, and I thought I was being pretty clever by saying that it was actually I think it was a fourth degree polynomial function. Unfortunately, that doesn't quite cut it because this is a linear function. So although it connected the dots really well, but data fitting is not about connecting dots, I guess. So anyway, so what we had to do, or what you suggested, and I did, was some of these. Probably traveled an extra 360 degrees, a full a, a full a full extra phase, and some of them might even have traveled an extra two. And so, like there, we have 720 degrees extra that it went that obviously cannot be captured by the polarizer, which made the data fit pretty nicely. And this is not this data has not been propagated. The errors haven't been propagated yet, but we can already see that most likely then our slope, which is our value for. Let me go back to. Which page? So we're plotting L pi divided by lambda, and so the slope is the difference in index of refraction right and left. So that's that. So the first thing I did was I took our data and I propagated it here in Mathematica. Let me find that. So I put in each of our L value lengths, and then I added, and I did not personally do the measurements, so I added an extra millimeter as potential error for interior dimensions for each container. So containers that had lengths that had 3 containers of usage had 3 millimeters of potential of error. So probably quite a bit. Probably too much. I was probably too conservative there, but that's what I tried, and it seemed to work. And you'll see in a moment here. And then our wavelength here, also part of our calculation, is 532.2 nanometers, and I just put a nanometer for error for wavelength. Now we can see what I did here to propagate the error. I did L times pi, and there's obviously no error in pi, and then divide that by lambda. So as we can see, we got these nice histograms about that would show the various potential values statistically that 10,000 data points could have. So nice histograms, and then when that leads us then to our means. And these means aren't very meaningful in and of themselves because they're set up so that our slope is directly that delta n value, and then our standard deviations. So what I did is I put those all back into another Excel chart on page 2. There we go. We have length times pi divided by lambda. So that's our x variable, and then we got our y is our rotation, and then our air. Then I put that all into Mathematica. And then so went through that. And you can see our error bars are pretty big, obviously. So I probably was, like as I said, probably overly conservative in how I and how much error I said we probably had. So you can see very large error bars. Well, that's okay. Um, um, but and then once I plot the data with the and then find the best fit, and then what we find is that we've got a 7.7 times 10 to the negative fourth is our mean value for that delta n, with a confidence interval of 6.5 times 10 to the negative fourth, all the way to 8.8 times 10 to the negative fourth. Again, we probably could have narrowed that down with a little bit less of a conservative error measurement, or error approximations. So anyway, so that is the conclusion then, of this research, or of this lab, um, is that there is a very slight 7.7 times 10 to the negative fourth difference in between index of refraction, between the right and left polarized. And one thing just to point out is that that value actually, despite our conservative measurements, if we go back to our Excel chart, is actually quite similar to what the slope there said, was 8 times 10 to the negative fourth. So actually we were right in the ballpark there, even without the non-propagated error.